Unit 10.6 is arc lengths and areas of sectors. Arc lengths and areas of sectors. A sector of a circle is a region bounded by two radii and an arc of the circle. A region bounded by two radii and an arc of the circle. As is highlighted there, shaded in the picture there, and it looks like a slice out of a pizza, you see. Okay? Now, if we wanted the length of an arc, the length of an arc, that arc is a part of the circumference of the circle, you see. Or we could say it is a fraction of the circumference. Now, if we were dealing with degrees, we know a circle is 360 degrees. And so when we want to find the arc length, we say that the length of the arc is equal to the arc measure over 360. It's that fraction of the circumference. So it's arc over 360 times pi times diameter. It is a fraction. It is a fraction of the circumference. Is the way I like to think of it. It is a fraction. What fraction? Well, the arc over 360. Of means times the circumference, which is pi times diameter, a fraction of the circumference. Okay? So if we wanted to find the length of arc AB in this circle, we would put the arc measure 70 over 360 degrees times pi, which is 3.14, times the diameter. If the radius is 6, then the diameter would be double that, 12. Okay? And that was measured in centimeters. So if we go to the graphing calculator and punch that in, we would have 70 divided 350 divided by 360 times pi times 12. So 70 divide 360, arc over 360 times pi 3.14 times the diameter, which was 12, 7.33 rounded. Any questions on that? Okay. The length of BC. The length of BC. If we wanted the length of arc BC, we would put its arc measure 120 over 360 degrees times pi, which is 3.14, times the diameter of 12 centimeters. So we would have 120 over 360 is a third of 12 is 4. 4 pi is 12.56. So we would have 12.56 centimeters. Okay? 12.56 centimeters. If we wanted the length of arc AC, we would take its arc measure 170 divided by 360 times pi, which is 3.14, times the diameter, which is 12 centimeters. We'll do that one in the calculator. 170 divide 3 times pi times 12. $17.68. Okay. So an arc is a part of a circle. To find the length of the arc, then you would find a part of the circumference or a fraction of the circumference. So we put arc over 360 times the circumference formula, pi times diameter. All right. Area of a sector. Now the sector is that whole slice of pizza, and if you want to find the area of the sector, it's a fraction of the entire area. It's a fraction of the entire area. So to get the fraction, we put arc over 360 times the area formula, which is pi times the radius squared. So the formula for the area of a sector is arc over 360 times pi times radius squared. We're thinking it is a fraction of the area. Okay? A fraction of the area. So we're going to find the area of each of these sectors. To find the area of the small sector, we're going to put its arc, which is 60. We're going to put its arc, which is 60, over 360 times pi, which is 3.14, times the radius, which is 8 centimeters, quantity squared. Now, we're going to get 64 square centimeters there, right? 64 square centimeters when we do the exponent. So we're going to throw this in the calculator. 60 divide 360 times. So 60 divide 360 times, I don't know why I just forgot it, but I did, pi times the radius, which was 8 squared. There we go. I just needed to think. Times pi times the radius, which was 8 squared. So arc over 360 times pi times radius squared, 33.49 rounded. Okay. The medium-sized one. Well, the medium-sized one had an arc of 124. So we would put arc 124 over 360. It's that fraction of the area. And area is pi times the radius, which is 8 centimeter quantity square. So we can do 124 over 360 times pi times 8 squared. We could hit second entry and it'll bring that back up. We want the first to be a 124. So we want to insert a 1. Want to get off and back on. We're going to change that to a 24. Everything else was the same. 69.22 rounded. And the unit was centimeters. We're dealing with area though, right? And so we had that centimeter square. So square centimeters, excuse me. The area of the larger sector, its arc was 176. So 176 over 360 times pi, which is 3.14, times the radius square. So we need 176 divide. We're going to go back to the calculator. We're going to hit second enter again, which is entry. We'll change that to 170, whatever it was. Six. Everything else is the same. We hit enter. 98.25. 98.25 rounded. Centimeters square, or square centimeters. Okay. So we've taken a look at an arc length. An arc is a part of the circle. It's a fraction of the circumference. We looked at the area of a sector. It's a region bounded by two radii and an arc. Like a slice of pizza, it's a fraction of the area. So we put arc over 360 times the area formula pi r squared. What we're going to look at now is the area of the shaded region at the end. And what this kind of reminds me of as we talk about that piece of pizza, there's a lot of people that won't eat their crust. So if you had that slice of pizza and you had that whole sector, but you didn't eat the crust, a lot of people nibble across there and they throw that little piece of pizza away and the crust with it. And so we're going to be trying to find the area of that shade. I used to do a pizza lab in my classes. They liked the pizza. They weren't as interested in the work, but we would divide the pizzas out. People would have to they'd have a group that their pizza they would have to find the angle measure of their slice, and we would find these little areas of the shades. We'd get the area of the whole circle, and we'd find out what percentage of the pizza was wasted if you ate straight across there and chunked that away with the crust. Anyway, gave us a good reason to eat pizza, and they actually learned some stuff too. All right, area of the shaded region. Now, that shaded region is that whole blue sector minus the triangle. So if we want that red shade, then we would have to take the area of the sector minus the area of the triangle. If we put in the formula for each, the area of a sector is arc over 360 times pi times radius squared. And the area of a triangle is 1/2 base times height. So to get the area of that shaded piece, we would have arc over 360 times pi times radius squared minus 1/2 base times height. Area of the sector minus area of the triangle. So, example, if we want this red shade, then we have to find the area of the sector minus the area of the triangle. So we're going to take the area of the sector, which is the arc 60 over 360 times pi, which is 3.14, times the radius, which is 4 centimeters squared, minus there of the triangle, which is 1/2 its base times its height. Now, we don't really have the base and height. The base would be this flat part, and the height would be from the center perpendicular. Now we do it that way because if one radius is 4, the other radius is 4, and that gives us an isosceles triangle. And when we draw the altitude to the base of an isosceles triangle, we know that it bisects the base and the vertex angle. And so that allows us to find a lot of things. Now, if we take that and take a peek over here, you see that if we were to turn that upside down, in other words, we set it on its bottom, as we would do to find the area of a triangle, then because of the isosceles triangle theorem, then this altitude that we're looking for bisects the base and the vertex angle. Now, The angle was 60 because the arc was 60. The vertex is the center. If the vertex is the center, then the angle is equal to the arc. The bisector of the vertex angle of an isosceles triangle is perpendicular to the base at its midpoint. So that 60 got cut into two 30s. Now that's a little bit hard to see, so I'm going to come over here and just take the one on the right and blow it up just a little bit. So what we have is a 30, 60, 90 triangle, and we know that that's 4. In a 30, 60, 90 right triangle, the hypotenuse is equal to short leg times 2, and the long leg is equal to the short leg times the square root of 3. Now what we know is the hypotenuse. So hypotenuse 4 equals short leg, which I'm going to call x times 2. So we divide by 2, and we get short leg x equal 2. So this is where the little 2 came from, here and here. And so that whole thing is 4. And so the base of my triangle is 4. Now I need the height of my triangle. The height is the long leg over here. So the height, which is the long leg, is equal to the short leg, which we just found out was 2 times the square root of 3. And so the height is 2 square root 3. I'm going to take this picture out and rewrite that, 2 square root 3. So we had a little bit of manipulating to do. I'm going to get some things out of the way so we can kind of focus on what we did. We said, okay, I want the area of this little red shade. So I'm going to take this whole sector minus the triangle. Sector is arc over 360 times pi times radius square. Triangle is 1/2 base times height. I didn't know the base, blue. I didn't know the height, green. But I knew if this arc is 60, that angle 60. And that's the vertex angle bisector, so those are 30 and 30. So I flipped it over on its bottom. We used the 30, 60, 90 triangle formulas to find the base and height. We plug them in, and now we can find area. Now we're going to do the first part and then the second part, because the second part has the square root of 3 on it. So we're going to do 60 divide 360 times pi times the radius, which was 4 square. That gives us the area of the sector. I'm going to go ahead and hit enter. 3.373 rounded. Minus half of 4 is 2 times 2 is 4 square root 3. Any questions on that? Okay. We want the area of the larger. So we want the area of this larger amount of shade. So we would take the area of the entire sector minus the area of the triangle underneath the sector, or underneath the arc, the shaded region, excuse me. This was 120 degrees, so my central angle is 120 degrees. I'm going to kind of draw that a little bit bigger. This whole angle was 120 because the arc was. That's the vertex angle bisector. So we're going to have 30, 60, 90 triangles that look like that. Now, the radii were both 4. We want to find the area of the shade, which is the sector minus the triangle. So the area is the sector, which is its arc, 120, over 360 times pi, which is 3.14, times the radius of 4 centimeters quantity square, minus the area of the triangle, which is 1/2 of its base times its height, and we don't know either one. Now what we know is that the hypotenuse is 4. If the hypotenuse is 4, the short leg is half of that because the hypotenuse is short leg times 2. Long leg equals short leg times the square root of 3. We should be to the point where we can just do that. The hypotenuse is 4. The short leg is half of that, 2, because the hypotenuse is twice the short leg. Long leg equals short leg 2 times the square root of 3. If that's 2 square root 3, this is 2 square root 3 because of the isosceles triangle theorem. So the whole base is 4 square root 3. So the base is 4 square root 3, and the height is 2. So we're going to do the whole first part. 120 divide 360. Times pi times 4 squared. There it is. I moved it down. I couldn't find it. 120 divide 360 times pi times the radius of 4 squared, 16.75 rounded, minus the triangle. Half of 2 is 1 times 4 is 4 square root 3. Any questions on that? In the unit of measure, square centimeters, okay? So we've got the area of a sector, the area of the shaded region between a triangle and a sector, and an arc length. That brings us to the daily work. We have 2 or 3 of this same scenario. And then we've got a bunch of other little things. So let's just come in here and let's just do the first set. We want the length of arc AB. To find the length of arc AB, you put arc measure over 360 times pi, which is 3.14, times the diameter, which is twice the radius, which is 10 centimeters. And we'll let you calculate that. What percentage of the circumference is that? How would you find that? 80 divided by 360. Do what it says, divide. When you divide, you're going to get a decimal. Let's do that on the calculator. 80 divide 360. So we're just going to change that fraction to a percent. 80 divide 360. Move your decimal 2 places. 22. You have a repeating 2, so you put it over 9. 22 and 2/9%. Okay. So there's some arc lengths. You can keep that going. Area of sector. Find the area of a sector, the small one. This is number 5. You would put the arc measure. The smallest one was 60. So we put 60 over 360 times pi, 3.14, times the diameter. The radius is 4, so the diameter is 8. Wrong. It is 8. The diameter is 8. I'm finding area of sector. The area of the sector is a fraction of the area of the circle. So it's 60 over 360 times pi times radius square. Radius square. And so we're going to go 60 divide 360 times pi times 4 squared. We get 8.37 rounded square inches. Okay. We want the percentage of the area. To find the percentage, you would do 60 divide 360. You would get 0.16 repeating. You move your decimal 2. You would have 16 and then a repeating 6. You put your repeating number over 9 and reduce. So it's 16 and 2/3%. The concept of repeats is on page 24 of the Algebra 1 book, where we looked at real numbers and integers, whole numbers, rational, irrational. Okay? And you can continue filling that chart out. Area beneath the shade. Let's find the area under shade DC. We didn't do one like that. Well, it's like it, but not with the same kind of triangle that we're going to create. Under DC. So we're going to want the area of the whole sector minus the area of the triangle. The area of the sector is arc over 360, 90 over 360, times pi r squared, because it's a fraction of the area. So times pi, which is 3.14, times the radius, which is 3 millimeters squared. We're going to have to take out the triangle, which is 1/2 its base times its height, and we don't have its base and height. But this is a 90-degree arc, so that would be a 90-degree angle. The radii are equal, so it's an isosceles right triangle. If two sides of a triangle are equal, then the angles opposite those equal sides are equal, so these are both 45. Now that doesn't mean it bisected the angle ADC. It did not bisect angle ADC, and it did not bisect angle BCD, but those are 45 because it's an isosceles right triangle. Now, if we extract that, here's what we've got. If we make this base, then the other leg is the height because it's from the top straight down to the bottom. So one of our legs was our base. The other leg is our height. Now you're going to be looking for 30, 60, 90 triangles, 45, 45, 90 triangles, or you may even have to do sine, cosine, or tangent. We're going to do the first part here, 90 divided 360 times pi times 3 squared. Times 3 squared. 7.065 minus half of 4 is 2 times 4 is 8. It's not going to work very well, is it? Because that's a negative. Let me check my calculations. I did something wrong, didn't I? I apologize for the delay. I paused it just so I could see. I can't believe I did this. You probably already knew I did this if you're watching. This is 3 millimeters, and I wrote down a 4. So the base and height are 3 and 3 instead of 4 and 4. I'm not real sure where that came from. So we're going to have half of 3 times 3, which is half of 9, which is 4.5. And so we get 7.065 minus 4.5. Is 2.565. 2.565. And it's measured in square millimeters. Any questions on those? We did one of the arc lengths, found a percentage of the circumference. We did one of the areas of the sectors, found the percentage of the circumference, and we found one of the little shaded regions here. This page gives us just more practice of the same things which you need. And so that ends the lessons of chapter 10. We have the odd answers to look at also totally worked out. And then we'll record the chapter review momentarily, the study guide.